For this assignment, I chose to model the effect that a winglet would have on velocity, lift, and drag. As a consequence of moving through a 3D medium, wings generate induced drag and vortices in the current behind them. The induced drag increases the amount of fuel one has to use, driving up costs, and the vortices pose a significant danger to anyone flying close behind the plane. The Valkyrie XB-70 disaster was a perfect example, where an experimental bomber generated wingtip vortices so large that it caused one of the planes following it to spin out of control and collide with the bomber, destroying both planes. Therefore, it is within one's interest to reduce both the drag and the vortex strength, and I've decided to model a winglet and use CFD to look at the velocity vectors at the wingtip. A winglet is designed to increase the wing's aspect ratio and drive down the induced drag. This should also decrease the magnitude of the vortices that are generated by the wing's edge. To demonstrate this effect, two wings were made with the NACA 0015 profile in SolidWorks, one with a standard edge and one with a winglet on the end. Both of them were designed to be 42 inches long with a 12-inch profile. The induced drag coefficient is dependent on the aspect ratio, the equations for which are displayed here. The analytical values calculated for those are 3.5 and 0.002625 for the standard wing, and 3.619 and 0.00254 for the modified wing, respectively. The compressible Navier-Stokes equations were used to approximate the flow values due to the wing's travel through compressible air. A transient system with a K-epsilon realizable viscosity model was used to model the vortices coming off the wingtip. The operating pressure was set to 0 psi so the solver could use the absolute values in the calculation. The working fluid was ideal air with the Sutherland viscosity model. The far-field inlet and outlet were given static pressure values of 10.594 psi, a Mach number of 0.7, and an angle of attack of 1.55 degrees. The system was then discretized in implicit form. I chose this format to increase the stability of my solution, and it was run for 40 time steps with a time step size of 0.001 seconds. According to the velocity plots, both wings demonstrate vorticity far away from the wing's surface, but strangely, there is no vortex propagated behind the tips of either wing. However, the drag results show that while the winglet drag is higher at first, at about 400 iterations, it becomes lower than that of the standard wing. The lift results also show that the winglet lift is consistently higher than that of the standard wing. The numerical solution for the drag coefficient for the standard wing was 0.00728, and the numerical solution for the modified wing was 0.002167. The lack of the vortices behind the wings may have been the result of the far field not being large enough or extending far enough in front of the wing, or not enough time steps being taken. Both situations would mean that the flow wouldn't have time to fully develop, and therefore not generate a strong enough flow to create vortices behind the wings. The increase in lift on the modified wing may be due to what is essentially a lengthening of the wingspan. An improvement in the design could include optimizing the winglet so that its profile is thinner, which could further reduce drag. The numerical drag coefficient solution for the standard wing seems very high, which could be due to an imperfect meshing of the wing's surface or the usage of outdated or corrupted data.